recording. So it's kind of an interesting topic because it doesn't seem like it would have many meaningful applications, but the applications of this topic are numerous, to say the least, right? So especially in the world of physics. But for now, we're just going to kind of focus on the geometry applications of it. So we'll just kind of live in that realm for the time being. And it's a pretty straightforward process. It's just what ends up happening is, and you know, it's a pretty straightforward process. But what ends up happening is students on the day of a test, they just kind of lose track of it. You know, they see graphically find u plus v, and what they end up doing is they just take the u and the v, add them together, get an answer, and then plot the points. And that's all well and good. The problem is that's not what I mean by a graphical solution, right? I'm just gonna resize this a little bit. Get it over here so I have a little bit of extra room. So what I mean by a graphical solution is using properties of geometry to get a vector sum, all right? There's two types of approaches that we can use. One is it's a triangular approach. Some people call it the tail to tip method. And another approach is the parallelogram method, all right? You know, different areas use different techniques. If you're in a physics class, most likely you would use the tail to tip or the triangular method. And I'll show both ways. And honestly, I'll even take that as a typo because I probably should have set this up to be ready to go to show both ways with two diagrams. So I'm going to do that now, but for future reference, I'd like to have some kind of reminder that I need two diagrams. So that's the bonus opportunity that comes into play for you all. All right, so and you know, it kind of it softens the blow when I do something like this and I just do a quick copy paste when you have to redraw the entire thing. You know, it's kind of aggravating. Right? But in theory, you're probably drawing both of them to begin with. So I'll show I'll show the triangular approach first, and then after that I'll get into the parallelogram approach. Right. So if you're in a physics class, you're probably learning the triangular approach, and the reason why is in most cases the physics teachers do not have confidence that you know geometry. You know, because it's not necessarily a prerequisite for a physics class. So they try to stay away from anything that's too specialized in the world of mathematics, and they kind of teach it from the ground up, which is why when you have formulas, if you remember in Calc 1, Calc 2, you probably learned some sort of justification for things like the position function, which we'll actually get into a little bit more in this course, velocity models, acceleration models. But in a physics class, you're generally just given those formulas, right? In this class, we'll talk about things like angular velocity, and we'll actually derive that using vector operations. So it's pretty cool, but in a physics class, you're just given the formula and you're told to plug and chug away. Here, we're kind of more concerned with not only how, but also the why, right? So when we're applying the tail to tip method, what we do is we replicate. And I'm going to turn off my lasso tool here so I don't have any issues. But we replicate one of the line segments and drag it so that the tail of that vector is at the tip of the corresponding vector, or the other vector, just to use simpler terms, right? So this is the same vector. This is vector u. I just moved it, right? And so what we end up with, if I'm looking for a resultant vector or a vector sum, is a line segment, which will become a ray once I once I get around to it, that line segment, that if this were a right angle at B, so at this particular location, if that were a right angle, we would call that line I just drew a hypotenuse, but it's not a right angle, so we wouldn't call it that. But it is the resultant side, and that would be the measure of U plus V. All right. Now, in terms of the actual sum, this point right here, that is the sum of the two vectors. So if we actually compute it out by hand, very simple process, 2 plus 4 is 6, 3 plus 1 is 4. If I were to, let me just double check, if I were to just count up boxes, I should end up with a 6, 4, all right? But what you may not know going in, and it's kind of aggravating, because I got this from I created this myself on GeoGebra and then pasted it in, but the labels came out so minuscule on the axes that I just got rid of them. So it's kind of hard to tell that these are supposed to be scaled by every half unit. So this is really the 1, the 2, the 3, and the 4. Right. So when we're plotting vector B, that's how we got there. All right. On the y-axis, it's 1, 2, 3, 4 single whole units. All right. So that makes the point at B 4, 1, which makes vector B 4, 1 with the triangular brackets. All right. So what does that mean? It means that if I want to go the rest of the way to this brand new point, I'd have to go, here's 5, and then here's 6. And then I'd have to go up, and I'll just use a dotted line. I'm actually going to make a dotted line after the fact using my eraser tool, or dashed line or whatever. Yeah. So all right, so it's 6 over, 4 up, so that corresponds with a 6, 4. All right, coordinate 6, 4, but vector 6, 4, which would be the sum of UV. All right. So, and in reality, I shouldn't gloss over things too much. This really is the coordinate 6, 4, so I don't want to get too lazy with my notation. This really is coordinate 6, 4. U plus V is actually the vector 6, 4. All right. So, you know, I don't really want to cut corners too much with this, right? So that would be the tail to tip approach or the triangular approach. Either way, I think the names, whatever name you choose, makes sense because I took the tail of one vector and I attached it to the tip of another, maintaining the orientation and the size. So whenever you maintain orientation and size, so through a translation, you're looking at a rigid motion. So you might remember that from geometry back in the day. But the same would hold true for, you know, basically anything other than a dilation where you increase the size, right? So you could call it the tail to tip method or the triangular method because, hey, guess what? It's a triangle. So that works out perfectly fine, right? Another technique, which is less popular with the physics students because they're more comfortable with the method that I just showed. You know, so that tends to aggravate people. It's like, I don't want to use your parallelogram method. I know it the other way. Can't I just do it the physics way? I always hear it the physics way. You know, that's the crazy thing. It's like, it's the physics way. It's not really the physics way. It's just another way. You just happen to learn that way in a physics class. All right, and so there's really nothing more to it than that. They're both mathematical techniques. It's just this one relies on properties of parallelograms, right? So if I replicate the sides of the, right off the grid. Oh, it's like right there. I think I could live with it. We're gonna see in a second. So replicate one side and apply the tail to tip method, replicate another side, apply the tail to tip method, and what you end up with is a parallelogram. All right, so it's essentially the same idea, except I'm including another side. All right, the diagonal of that parallelogram is your resultant vector. All right, that vector u plus v. All right, so honestly, I don't know. It really amounts to the same thing and just throwing another side in there, right? So it's like, did I need that extra side in order to create that diagonal? Probably not. But the benefit of doing it this way is it establishes that that resultant vector is going to work as the sum of two vectors regardless of the orientation. Okay, so we have v followed by u, and then also a u followed by v. It's establishing the commutative property of vector addition, right? So it's a pretty cool observation, but also it's a necessary one, right? So when I ask you, and I will ask you, just to be transparent about pretty much everything on the test, to graphically find the sum of u and v, I'm looking for one of these two techniques, all right? Now, again, what do you do in order to find the sum? You do the same thing we did for the last one, right? So you establish, okay, we got 1, 2, 3, 4. And it went off the grid based on how I cut it, but we can assume that this is 5, and right at the edge here is 6. You know, maybe a little bit over for the 5. And then you got your 1, 2, 3, 4. All right, so this is the same relationship. All right, those are dashes, not negatives, but I didn't want it to conflict with the other diagram. But you can see here that we are looking at a coordinate at 6, 4, which corresponds with a vector sum of 6, 4. All right, so either way. Now, I don't have any delusions here. I know the people who are going to just add the vectors and know what the answer is going in. That's what I want you to do. I want you to know what the answer is before you even start, but I also want you to demonstrate that you know what a vector sum is, right? And it's not me being particular or nitpicky or anything like that. People in the past have thought that. They're like, I knew what the sum was. Why was it so important that I get this? It wasn't so much that I cared about you demonstrating this one particular skill on one particular assessment. It's more so that you're going to need this skill. This skill is going to become more and more important as we go on. So when that happens, I just kind of want to force you to study it now, so that later on when it becomes really, really important, you've already done the work, right? So I force it now so later on you don't get bogged down with the minutia. Or you're playing catch up, which is even worse. You know, like that whole unit circle thing, right? Based on the number of unit circle bonus assignments that I've seen submitted, I'm going to say that maybe we got some work to do on that unit circle. Right. So, and then of course there's always the people or two that are like, wait, there's a bonus assignment for unit circle? Yep, there is. It's in the unit 1 folder, and I got to double check, but I'm pretty sure I still have it open. Right. If not, then I'm just a big liar here. But I wanted to keep it open. I wanted to keep it open right up until the first unit test because it's important stuff. And so the idea always comes back over and over again that if you got that unit circle down, it's going to carry you a long way. So I'm just forcing the issue. I'm making you study it, even if it means I got to give up a couple of bonus points in the process. Yeah, this baby's still alive. I'm just going to edit column information, just make sure. Yeah, 10/7 at midnight. Right, so I'm even giving it until after the test, but that's an old reference. But shutting the barn door after the horses already got out, that's not always an analogy that resonates with people, but you get the idea. Like, what's the point of shutting the door if people, if an animal has already escaped? Was there a question?
What day is our test again? Sorry.
The 7th.
The 7th. So, okay, I should write that down.
So that's a week. Yeah, it's all in the syllabus. So the dates for all of the unit tests are in the syllabus. So if you look at that, you can just pop it all into a calendar and you'll have them ready to rock and roll. Right. So yeah, definitely getting closer and closer. Right. And so with that in mind, if you haven't had an opportunity or you haven't started looking at the review for the test, you may want to take some time and do that. Right. So, but yeah, that's not something that's mandated just yet. But the closer we get, like towards the weekend, into early next week, you're definitely going to want to do that. Right. So, example A in the next category, it says, given the vectors V and W shown, sketch the vectors 3W, V plus W, and 2V minus W. These are vector operations, but specifically graphically. And so right here, you can see how if I wanted to really be a monster on the test, I can give you a question where you have to geometrically figure out the vector sum, and you would have no hope of figuring it out just numerically by taking the 2 and the 4 and adding them, the 3 and the 1 and adding them. You'd have to do it using one of the techniques that I just showed you. But sometimes they're really easy, like 3W. So how would you handle something like that? It's actually super easy, barely an inconvenience, because this is what W looks like. So I just need a line segment that has the same orientation as W. Right, so I'm a little off the mark there. So let me, and it's a little too hard to kind of get it perfect with this. It's kind of rocking back and forth on me. So I'm just going to kind of live with it the way it is. It's right there. It's close enough. So this has the same orientation, and it also has the same length. All right, so that's what W is equivalent to. So what I do is I just kind of pull that off on the side. If you're using an app, it's easy. If you're doing it with pencil paper, it's still not that bad. All you'd have to do is get a index card, something like, just draw a little index card. So pretend that's an index card. You match it up with the figure, mark off the index card at the appropriate length, then slide the index card over to where you want to draw your drawing, then draw a line segment, then slide it down, draw another line segment, then slide it down and draw another line segment. Right? So that's all that's really happening here. But if you have an app, and there's a benefit to having one, like the GoodNotes app that I'm using, you have the ability to do it without really putting too much effort into it. Right? So digital ink is on the table. If when I give you the test problems, especially the ones that require handwritten work, the multiple choice, you just put your answer in and hope for the best, and it's really not that terrible. But multiple choice is pretty straightforward. The free response could be the short answer kind, or it could be something where you have to show the work. And if it's a case where you have to show the work, then doing it with the digital inking option is actually a pretty nice way, because then you can just share a PDF version of what you got and just dump that right into Blackboard. All right. But again, all I did was I used an index card. So if I'm doing it by hand, I use an index card. Even make it obvious, this is an index card, or a side of piece of paper. Mark off the distance on the edge of one side, and then just go where you want to draw it, sliding it, not picking it up and changing the orientation. The orientation matters. Right? So sliding it over to where you want to start your drawing, make a little mark, right? Then at that mark, slide down, make another mark, and then make a third mark, because this one is 3W. All right, so 3W. Right. V plus W, that one, not too bad. Not too bad at all. So we have V, which I'll do in green. That's going to be that length. Kind of bring that over here. We'll bring in W. label them up so I don't lose track of things. Right, that's really more for organizational purposes than anything else, because if you have the orientation down correctly, then we're not really concerned about anything other than, you know, like the figure itself, the labels I don't get too bent out of shape over. But it's never a bad idea to include the labels, especially if you're not using color like I am, because if you skimp on the labels and it's not easy to discern what part is what, then we could have a problem on our hands. My brain always takes me to the parallelogram approach, so that's what I tend to do. All right, and so the two endpoints, you have the intersection between V and W, and you have the intersection, the vertex on the opposite side, right? V and W. Oh, check that, sorry, apologies. I lost track of the orientation of W. I don't know why I'm laughing about that. That sucks, it's terrible. I threw myself on the mercy of the court. Question?
No, I was just gonna tell you the direction seems.
Tell me the thing I screwed up. Yeah, thank you. I appreciate it. It's one of those moments. It happens, but you know, just be mindful. I'm usually the one that's got to worry about that the most, but be mindful of the direction of the arrows. Yeah. And so when you're doing the tail to tip. Oof. All right, and so we got that. And I like to do the copy paste job here, because if I'm copying and pasting and sliding the opposite side in, and it ends up being the parallelogram that it ought to be, then I can be pretty confident that I did it the right way. You know, it's only when you start freehanding things that you end up in trouble. So you're going to want to use a straight edge. You don't have to go out and get a ruler if you don't have one, but some sort of straight edge has got to be used here. Otherwise, you're going to introduce an unnecessary or unacceptable and really unnecessary amount of error, right? Because the error doesn't need to be there. You just only need to include a ruler, a straight edge. But the error that you will be introducing will be an unacceptable amount, right? And on a test that translates to point deductions, and we don't want that, right? Not for that. We never want point deductions, but we don't want it for like simple things. V plus W, I almost said U plus V, force of habit. All right, so just label it up. V plus W is your vector sum. It's the resultant vector, the diagonal. Again, if you did the tail to tip, that's fine too. But again, this is the way my brain works. I'm just going to move some things around. The last one has a size dilation involved in it. So, that involves a little bit of extra doing. I'm just going to move my index card over here. Kind of like having the index card involved. Feel like it's that's a little safety blanket. All right, so for C, I need 2 times the length of V and then minus W, but really that's 2 times the length of V, that's not a V, 2V plus -1 W, all right? So we don't really talk about vector subtraction. We mentioned this last time. We talk about addition with a negative scalar, right? So what this negative here is telling me that the W is going to be going in the opposite direction, right? So we're going to reverse the direction of W. But we're also going to double the length of V, right? So I got a V here, and I'm going to get a second V involved. And I'll slap a little arrow on it. Try to line it up the best you can. There we go. All right, so that's 2 V's. Now I need a negative W. All right, so the negative line segment for W, I could just steal one of the ones that I already drew. Now it's going to be going in the negative direction from the intersection between the two. So this is going to be negative W. All right, so instead of going downward like it did originally, it's going to go upward and to the left. All right, now I'm going to find the vector sum here, and when I do that, I'll have it. All right, so I'm just going to move some things around. Just a smidge anyway. And then when I create my opposite sides here, I want to grab all of my 2b. Move that over here. And then all of my negative 1w. I like to have my labels on the outside where possible for the initial vectors, but for the resultant ones, I like to have it on the inside. All right. We have the vertex, the original vertex, and it's going to go to the opposite vertex in that parallelogram. So close. And there it is. All right. So that would be my 2v minus w. And all of that is done geometrically, right? So, you know, like I said, it takes a little doing, a little organization, but it's really not that bad. And again, you know, like if you're using an app, even easier. You know, that app doesn't have to be anything too monumental. If you want, I know that this GoodNotes app has a free trial version that you can annotate one document, not like one document forever, but like one document at a time. And so if you wanted to, for like a test, you wanted to do your work using something like this, an app like this, you can get the GoodNotes app for iOS devices, or if you have a MacBook, it works on MacBooks also. And then, you know, do your scratch work on this app, and then use that as, you know, export it out or take a screenshot of it and submit that work. You know, it gives you the option to create all the colorful illustrations. It also it gives you the option to, like you've seen with me, screw up and then easily fix that screw up. All right, pretty important stuff. But you know, it's a matter of preference. So let me pause. So yeah, I got a whole spiel related to how that first test is going to go. What the circumstances are, and how it's going to function, and what your expectations are, and probably most importantly for a lot of you, what's going to be on it. You know, the review problem sets give you a good idea, but I also like to give a play-by-play, meaning question 1 will be this kind of question, question 2 will be that kind of question, question 3, and so on. So sit tight for that. That's coming. All right. We're going to talk about magnitude now. Magnitude of any kind of vector is really just the length of that vector, right? So that's not really a challenging thought process, because you've worked with the magnitude of vectors before. You just didn't necessarily realize that that's what it was. A magnitude, again, is a distance. It's a length along a coordinate system, right? So if I want to find the magnitude of vector v, the first thing I would do is draw a quick sketch, assuming that I was doing it by hand, like an old geometric technique, you know, going back to, you know, like 9th grade, -6, -8. So roughly about right here. I mean, so scaling's a little iffy, but this is what my vector would be. If I wanted to find the length of that vector, I can decompose it into the corresponding right triangle. We typically, just for consistency, we go to the x-axis when we do that, when we decompose. And so I know that this is going to be a -8. And this length will be a -6. we have a right angle. So I use a little Pythagorean theorem, a little Pythagoras action going on over here. All right, so nothing too crazy, nothing too fancy. All right, so I would just very simply and quickly and easily do a -6 squared plus, and I always say the simply and easily, and then I screw it up. So we just got to be careful. All right, so this is supposed to be vector v, but that vector v is going to have a magnitude. So we use a double absolute value bracket for that. So that length, absolute value squared. All right. So 36 plus 64 is 100. Square root of which gives you the absolute value of 100 is 10, or the magnitude is 10, right? So it really is another form of an absolute value symbol, right? The double bracket just means that the absolute is applying specifically to a vector, right? So it's kind of weird because you would think to yourself, well, then why do we need a new symbol? Why can't we just use the old absolute value symbol? And my answer to that is some people do. Some people will just write absolute value of v. I like the double bracket, not because it looks cool and sophisticated, but because it's a way of distinguishing concepts. Now, if I needed to take the absolute value, like ordinary absolute value, I wouldn't want people thinking that I'm working with vectors and vice versa, So I want my notation to be representative, right? So that's really what's happening here. That my symbols look pretty bad, so I'm gonna put a fresher looking ones in there. I mean, it's like weird that I care about this, but because we've all been in classes where the teacher absolutely does not care if their handwriting is legible. I probably care a little too much. Still doesn't help, but I do care. All right, so find the magnitude of vector v. Well, we got it. So that's our answer to A. Now we could use a shortcut. The shortcut is the formula. Now, if we generalize it, and I'll show you the generalization of it, because it's kind of, I'll say interesting, but it's really just nice to know the origin story behind these things. So, and especially for those of you for which this isn't really the last stop in your mathematical journey. Some of you that are just getting started, maybe there's some advanced calculus coming down the line, or, you might have taken differential equations, but there's a second level to differential equations called partial differential equations. You start getting into more and more proofs when it comes to those kinds of courses. And this actually is kind of one of the beginning ones, but it's nice to be able to get a handle on it prior to actually taking those courses, right? So all this is saying is if I have, instead of -6 and 8, I have A and B, I'm applying Pythagorean theorem, which isn't the complicated part. Oops, that went away. Yep, that's what I want. So A squared plus B squared equals C squared, but the C squared is really magnitude of V squared. Now, the only thing that we would need to do, and it's not a complicated one, that's the good news. Normally when I say proof, it's like, all right, buckle up, it's going to take a while. This is not one of those cases. I'm just going to take the square root of both sides in order to solve for the value of the magnitude of V, right? So I'm looking at here, the magnitude of V is equal to the square root of A squared plus B squared. All right, so that's the origin behind the formula. Nothing too fancy. It's all just Pythagorean theorem. All right, so that's good news. Now, if I wanted to use the shortcut, I could just pop it in there, but as it turns out, we've already done the work. So there's no need. So the magnitude of V is equal to 10. All right. So the big question comes about in B and C, because these look like two practice problems, you know, two standalone kinds of questions, but they're not really. They're really just trying to get after an idea, and that idea has to do with scalar multiples and whether or not they influence results of a magnitude computation, right? So we already figured out what the magnitude of V is. That's equal to 10. So for part B, that's very easy computation. It's just 5 times that result is going to be equal to 50. So what we're getting out of this is, if we have a vector, -6, -8, all right? So we have a visual representation of that. If we find that magnitude and then just multiply it by 5, what do we get? We get 50. Now, the other possibility is maybe we multiply the vector itself, a scalar multiplier of 5. So basically, take the length of that original vector V and multiply it by 5. So it's going to be quintuple itself, you know? So it's going to be really, really long, basically. You know, instead of 3 line segments like the last one, or 2 line segments, it's going to be 5 line segments. And then find, using the Pythagorean theorem, find the magnitude of that, all right? So 5V is equal to 5 times -6, -8, which in turn is -30, -40. All right. So if I want the magnitude of 5V, I'm applying the Pythagorean theorem on that. And I definitely don't want to plot -30, -40, although it wouldn't be too terrible, right? So the square root I really didn't need it to be that long, but whatever. So -30 squared plus -40 squared. All right. So that's essentially a 3, 4, 5 right triangle, but you can carry out the operations here. You're going to get radical 2500, which is going to be, it's going to end up being an even 50, as we expected. Or maybe not expected, but I'll say theorized, or it was that was what our inference would be, right? So it turns out that instead of, if I have a scalar multiple, instead of finding the magnitude of the larger quantity or the larger quantities, what I can do is factor out a scalar multiple, find the magnitude of the simpler vector, and then multiply it by a scalar multiple after the fact. It makes life a little bit easier when you have to run through the computations. All right. Not the kind of thing where you always have to really consider that. Sometimes it's just like, well, I'm going to do it in the calculator anyway, so it doesn't matter, you know. But if you want to crunch out numbers, you know, you're just, I don't know. Some of my analogies don't land, but I'm usually in the car just trying to figure out problems. Like, I have a moment of inspiration, and I'm like, oh wait, how does that? Oh, that's how that works. And then I'm sitting there being like, all right, well, so then carry the one, blah 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 blah. You know, I'm looking for the easiest way to do the mental math, because I don't want to sit there, you know, and pull the car over and draw a diagram, you know, slash draw the diagram while driving. You know, that's not a good habit. All right. So on the next page, we have all of these properties, which I said based on the highlighter here, and also my memory of it. Sorry, I get a little eyelash on the screen here. That these are important properties. Some more important than others, and well, they're all equally important, but some more important from a student perspective, in that they're not common sense. Like u plus v equals v plus u, we just kind of beat that one to death. But even if we didn't demonstrate it visually, we would still kind of assume that that would be true. Commutative property tends to transcend simple arithmetic. Same thing with the associative property. We also have the additive identity relationship. If I add the 0 vector to some vector u, then we end up with vector u. Let me actually take a second and show you that one. All right, so I'm just going to say 3. Yeah, my little the alignment's a little off. That's a typo. Yeah, fix that. All right, so the directions here. Well, the preamble: let u, v, and w be vectors in R to the nth power. That's not really what that means. It's Rn. Right? But what that means is real space nth degree. All right, so I'm going to make a note of that here off on the side. Rn real space nth degree. All right, so if I say R3, for example, real space 3rd degree, so 3 dimensions. All right, real space just makes it seem fancier than it is. You get into vector spaces, and if you have any experience with linear algebra, or if you're going to take linear algebra, these terms are going to come up over and over again. You got vector spaces, you got subspaces, you got the imaginary space, you got the real space, complex spaces. But anyway, the real space is talking about a coordinate system that's only made up of real numbers, so no imaginaries. The nth degree tells us how many dimensions, right? So if it's R4, it's the 4th dimension. If it's R1, it's a 1-dimensional situation, right? So in every one of these cases, in order to actually justify it or do something with one of these properties, I would need to at least have an idea of what kind of space I'm working in, right? So what I'm going to do is I'm just going to assume that we're looking in R2. All right, so R2, u plus 0 is equal to u. I'll just focus on that part of it. All right, now at first glance in the algebraic context, it looks like, oh yeah, of course, u plus 0 is equal to u. But if I tell you that u is a vector, and I did in the preamble, u, v, and w are vectors, then, and it's in R2, it's going to have 2 components that I'll call u1 and u2, which makes 0 the 0 vector. So I'll make a little note. Oh, actually, I was going to say I'll make a note, but I already did. If I highlight everything, it's like I'm highlighting nothing. So let me. 0 represents a 0 vector. All right. So you'd ask, well, how many dimensions would that vector have? Well, whatever it says. You know, we're working in R2. So it has to have, in order to add 2 vectors, you have to have an equal number of components. So there's 2 components to my first vector. So my 0 has to have, I'll highlight that in red, has to also have 2 components. So 0, 0. But if you're in 2 dimensions, you just think about it. If you're in 2 dimensions and you're at the 0 vector, which would be a vector that is squarely at the origin, but coordinates of the origin are 0, 0. So there's no reason to really doubt this, right? So when you add these 2 together by their components, u1 plus 0, comma, u2 plus 0, result u1, comma, u2, which in my very first step, I established that u was equal to u1 plus, or u1 comma u2. All right, so that allows me to do a little reverse substitution here and conclude that this is equal to U. All right, so that's that's one of the easier proofs when it comes to vector operations. I mean, working in R2, so it definitely made it a little bit easier, but I don't think there'd be anything to gain by doing this in R3 or R10. That's just obnoxious. You know, if I said do this in R10, you'd have to make a vector U1 comma U2 all the way up to U10, and then the zero vector would have 10 zeros, but it would amount to the same thing. All right, so there really isn't anything more to it than that. That's pretty much the nuts and bolts of it. But you can carry out a process like that to verify pretty much any of these properties, right? So let me do. I don't know. It really doesn't matter because they're all pretty straightforward. I'll do 7, I guess. And we'll do this. We'll do it in R2 again. All right. So U, V, and W. Well, W is irrelevant here, but U, V, and W are all vectors. So my U is going to be U1 and U2. My V is going to be V1, V2. All right. So I'll start on the left-hand side. C is a constant for a scalar multiple. So C, U plus V. All right, so that's going to be equal to C times vector U, which is U1, U2, plus vector V, which is V1, V2. I can get the sum by multiplying the corresponding parts. I think I might have said multiply, I meant to say adding. So C U1 plus V1 comma U2 plus V2. All right, so kind of working through with a little bit of computational skills, but also we're going to get into a little bit of distributive property in a sec. All right, so, oh, you know what? I don't want to make this too complicated. Let me go back a step. I'm going crazy here. It's just a distributive property. I almost put a hex on the whole dang thing. By the way, I forgot to say this earlier on in the course. Just about every kind of like weird quote that comes out of my mouth is some kind of movie reference. And I always give bonus credit for identifying the movie references, right? So I definitely forgot to say that. So I tend not to repeat them, but I do it like over and over again with different movie references. Ongoing thing. So if you catch one, send it in on remind, and you might get some bonus. You know, and I usually throw in some really easy ones for the people who aren't movie fanatics. You know, ones that everybody should know, because it's such a mainstream stuff. Right? Anyway, so sorry about that. But what we want to do here is distribute the C. Kind of lost track of the objective of this was, right? So I'm going to distribute the C to each one of these vectors. So I'm looking at C U1 comma V1 comma U2 plus C V1 comma V2. Right. And so in our first step, we established that U was the same as U1, U2, and V was the same as V1, V2, we had to establish that this was going to work. So it might have seemed like an unnecessary step, but we had to establish that this is going to work in R2 specifically. So it wasn't just a matter of distributing the C and calling it a day. That wouldn't establish the R space connection, all right? But now that we've distributed sufficiently using scalar multiple techniques, we can now convert this back to just a U, and this one back to just a V, with the C, and the plus, and then we have it. And I thought I had a typo there, but I don't, shockingly. Just looking for bonus points to give people, that's all. All right, so that's another example, a little bit less interesting than the previous one, but it's still an example of a proof. All right, so the example that follows, U and V are two non-zero vectors that are non-equivalent. Okay, so they're two different vectors, right? Two different vectors that also have different magnitudes, right? Consider the vectors A equals 4U plus 5V and B equals U plus 2V, defined in terms of U and V. Find the scalar lambda such that the vectors A plus lambda B and U minus V are equivalent, right? So a lot of weirdness going on with that one. So a good place to start would be through direct substitution, because we have this expression here that says A plus lambda B. That A plus lambda B has an A and it has a B. All right, stating the obvious here. But we have an expression that relates A in terms of U and V, and also relates B in terms of U and V. So I can jump right into a substitution kind of deal and say that 4U plus 5V plus lambda multiplied by B, which is U plus 2V, all right, the vector, find the scalar lambda such that the vectors A plus lambda B and U minus V are equivalent. So equivalent meaning mathematically equal. So this expression should be equal to U minus V. All right, with the idea that we're going to be solving for the value of lambda here. All right, so I could distribute first, but I think it's probably a better move to knock off the 4U. So simple algebra, knock off the 5V. So we have lambda U plus 2V is equal to negative 3U minus 6V. So then in my next step, I'm going to solve by dividing. And you see that this actually, I mean, this is kind of a tailor-made question, which is, you know, very academic. It's not a really a practical question, because in the real world, things just don't work out this nicely. But when I divide out the the U plus 2V, you get a clean cancellation. Might not seem like that right away, but I'm looking at lambda equals, if I look at the top here, I got a common factor of -3. When I factor that -3 out, I get U plus 2V. And then on the bottom, I have that common U plus 2V. So it turns out that the vectors U and V are irrelevant as long as this relationship holds. Lambda is going to be equal to -3. All right, so pretty nice outcome. I mean, it is possible that we could have gotten a lambda value that was in terms of U and V. you know, maybe there wasn't such a clean cancellation. And that would have been fine too. Well, what we would have had is a couple of free variables, and those free variables would have dictated what lambda would be, you know, but if we got lucky, it turns out lambda is equal to -3. All right, so this is kind of like a little bit of a taste of what's to come down the line, because we're gonna be working with this magical scalar value known as lambda when we get into Lagrange multipliers. All right, so that's a method involving partial differentiation. So, you know, we'll tie together our concepts involving what we're talking about now, vector arithmetic, and then also some differentiation techniques and integration techniques. It all comes together in a really nice way. All right. Trigonometry. Again, you see thetas, you see right triangles, and hopefully the first thing that pops into your mind is, wow, okay, I guess this unit circle thing is really, really happening. He wasn't kidding about that. Because it's like every time we step away from the unit circle, it's like having a bungee cord attached to you when you start walking away. A really powerful bungee cord, you walk away, you only get so far before you snap right back to where you started. And it's like, yeah, no, this is really happening. Right? So if you haven't made it your business to get to know that unit circle, to refresh your memory on it, then we're getting close to the I don't know what you're waiting for part of the course, right? But for now, it's, hey, you might wanna get on that, right? If we want component forms of a vector using trig, then we're gonna have to get some angles involved, right? So we have, in each of these cases, we have a vector. Now, one of them has a known vector quantity. That vector quantity is equal to 1, right, in that first triangle. But in the second case, it's equal to some unknown value, all right? Now, typically, when you're dealing with a horizontal movement, we call that x. And a vertical movement, we call that y, all right? There's nothing out of the ordinary there. We have a nice relationship, and that is x squared plus y squared is equal to 1 squared, or just 1, right? So that's nothing new. We also have some other things going on here, like, for example, trigonometry, Sohcahtoa, Sohcahtoa. All right. We always want to kind of involve the most convenient part of any relationship. So when we're dealing with the right triangle, most convenient part would normally be the one that you know, the quantity that you know, right? So I could say tangent of theta is equal to y over x, but I don't know if that's going to get me anywhere. But what I could start with is the cosine of theta is equal to x over 1, which makes x equal to cosine of theta. All right, so I can just kind of tuck that in down here. A nice little relationship there. All right, we also know that y is equal to the sine of theta, or at least it will be, because sine of theta is equal to y over 1, and it gives us, in turn, y equals the sine of theta. So now I have the vertical side, and I'm going to clean that up a little bit. Or quality equal sign there. So x equals cosine theta, y equals the sine of theta. All right, so we got that in, we got all that information, which is great. All right, we also know that cosine squared theta plus sine squared theta is equal to 1. And if you were wondering, that's actually the derivation of the Pythagorean identities, or the first of the 3 Pythagorean identities and their addendums. Right? So, addenda. So, we have that information, that's wonderful, but then it's a question of, well, how does this equate to the vector form, component form of a vector? If I know that any coordinate in space is the result of x comma y, then that corresponds to cosine theta comma sine theta for the coordinate, all right? But it also means that a vector, I'm going to resize a little bit here, create some more space. The vector xy, put that up to like a 0.4. Would correspond to vector cosine theta comma sine theta. All right, so what that tells me is that this vector, the one that is represented by the hypotenuse here, and I can do that with a nice arrow, is going to be measured at the value or the expression cosine theta comma sine theta. And its magnitude is going to be equal to 1. All right, so the magnitude, so this is going to get a little dicey, but I'm going to bring it in and try to do the best I can. So the magnitude of that vector, maybe we'll do a little resize. Actually, I'll resize them both. Kind of move that off. The magnitude of cosine theta comma sine theta is going to be equal to 1. All right. So that vector itself is just cosine theta comma sine theta, depending on theta. So if theta is 30 degrees, still going to have a magnitude of 1. If theta is equal to 170 degrees, still going to have a magnitude of 1. If theta is equal to 1 degree, still going to have a magnitude of 1. This 1 looks a little weird now, so I'm going to change it. A little bit better. All right. And so in short, it's a little too late for that, but what this is telling us is that the unit circle is actually a set of unit vectors in space, in 2 dimensions. So in R2 specifically. All right. So that's crazy. It's crazy and it's great. One reason why it's crazy is because it's like you're taking something that you learned about years ago for the first time, and in a lot of ways you kind of learned about it out of context. It didn't really have too much meaning. You were just told, okay, this is going to be really important at some point. All right, you better learn it because it's all trig. Every aspect of trigonometry relies on this one crucial piece of information. All right, so that was fine, and you believed it or you didn't. But then now I'm telling you, not only is it important, but it is a foundational component to any aspect of vector movement. All right, so anything about vectors, direction, movement along a path, or navigation, it all comes down to knowledge of the unit circle. All right, so incredibly important. Now, we get into a case where the magnitude is something other than 1. Well, if we think about our studies involving the polar coordinate system, which ties in nicely with this, we get at the idea that, well, that's just the same as having a radius other than 1. So then what ends up being the case is that x is not just cosine of theta. It would normally be r cosine of theta, where r is the radius, or in this case, it would be the hypotenuse. Right? So instead of that, I'm going to say the magnitude of v cosine theta. And y would be equal to the magnitude of v sine theta. All right? And we get that through the same operation. So we found cosine of theta is equal to x over 1. Instead of that, we would say cosine of theta equals x over magnitude of v, and then solve for x, and you get v cosine theta, magnitude of v cosine theta. Same idea for the sine. But really, from this, we get across the idea that any vector in space can be represented by this expression. The magnitude of v cosine theta, comma, magnitude of v sine theta. All right, so this is the component form of a vector, all right, in general terms. But even better, since magnitude is itself a scalar, I could say magnitude of v cosine theta, comma, sine theta. So little chuckle here because, you know, you see that cosine theta, comma, sine theta, and if it just registered in your mind, okay, so the only way I can get a question like this right is if I know the unit circle, then yeah, you're right where I need you to be, right? So this is the component form of a vector. Oop, I don't know why that P came along for the ride. There we go, much nicer. All right, so you got that. At a minimum, you have a formula. At maximum, you have a nice justification for why that formula exists. All right, and you know, I gotta say, any process that I take you through, where it's like, he's really covering all the bases on this, every fine detail, man. He's crossing the T's and dotting the I's. I can tell you that those are the cases that I didn't, when I was a student, I didn't quite understand them at first. And so I really worked to come up with a way for it to make sense to me. And so I'm just kind of paying it forward now, or passing it on. I don't think it's paying it forward. I don't think it's the right way to represent it. But that's the idea. So that's how important this concept is. That I'm like talking in slow motion to get this idea across. Right? It's going to come up over and over again. Right. The example is component form of a vector with a magnitude of 4. Right. So you can use vector v for vector. That works. Right. It's pretty standard. So the magnitude of v is 4, and it forms an angle of negative 45 degrees with the x-axis. All right. I like to draw a quick little sketch. I like to know where my vectors are living. Doesn't have to be a work of art. With me, it's not going to be anyway. So that's just the reality of it. All right. So this is going to be my value theta. Now, theta can be positive or negative values. So this just means that we went 45 degrees in the clockwise direction rather than counterclockwise. But if you want to make it a little bit more comfortable in terms of the unit circle, you could think of this as 315 degrees. Either way, you're going to get the same value. The negative sign was really bugging me. Now the disconnected ray is really bugging me. So I'm just bugged. All right. So if I want the component form, I'm looking at the magnitude of v cosine theta, comma, sine theta. So 4, magnitude should be positive. So we don't have to worry about it, you know, being a mysterious negative value. If there's going to be negatives in your coordinates, it's going to come from the cosine theta, sine theta computation. All right, so cosine, I'll go with the 315, and then the sine of 315. Both 45-degree reference angles. In the fourth quadrant, ASTC tells us that cosine is positive, sine is negative. So we're looking at rad 2 over 2, comma, negative rad 2 over 2. Multiply those two bad boys, and we'd be looking at 2 rad 2, comma, negative 2 rad 2. And it's really it. You know, it's just computational stuff. I mean, we'll get into the calculus associated with this soon enough, but for now, we got to get the skills down, right? Vector form of magnitude 10, a vector v with magnitude 10, so forms a 120-degree angle with the x-axis. So that's in the counterclockwise direction, so we're looking at something like that. And again, that's for me personally, the little diagram, because when I did the computation, I didn't mention it, but when I did the computation in number 1, I saw my final answer, positive number, comma, negative number. And then I look at where I drew my array in the 4th quadrant. If you plot a point in the 4th quadrant, it's going to be a positive number, comma, a negative number. So I'm pretty comfortable that I didn't just royally screw that up. If I screwed it up, it's definitely not royally. Maybe it's, I don't know what the opposite of royal is. Like peasantly screwed it up. I don't know. So we're looking at 10 cosine $1.20, comma, sine of $1.20. So just got to know your unit circle. Cosine's negative in the 2nd quadrant, so negative 1/2. Sine is positive in the 2nd quadrant, so positive radical 3/2. Multiply through, you get negative 5, comma, 5 radical 3. Again, super easy, barely an inconvenience as long as you know your unit circle facts. Oh, and they don't always have to be movie references. They could be YouTube references. They could be just any kind of media reference. So I've said super easy, barely an inconvenience like 30 times over the span of the course. So there's got to be something to that one. I wonder if maybe that's something you look up. Mm-hmm. So not too bad. Not too bad at all. So we talk about unit vectors. Unit vector is just looking for a vector that points in the same direction as a given vector. So another vector. So we're given a vector and we want to come up with another one.
Professor?
Yes.
I'm sorry, can you just go back for like a quick second? Let me just see.
Yep. So with a unit vector, we're looking to create a second vector from the one that we're given that goes off in the same direction, but has a magnitude of just 1. All right. So in numbers 1 and 2 here, we had magnitudes of 4 and 10 respectively. No problem. What I want to do here is take a given vector and write it in such a way that we're basically simplifying it so that it has a magnitude of 1. So the formula is U equals 1 over the magnitude of V times V itself. Or really, we could even say V divided by the magnitude of V. All right. So it's kind of, I mean, if you have any comfort or knowledge of statistics, it's kind of like along the lines of finding a z-score, where you have a measure that represents the scale of a value, like a standard deviation, and you divide that into the actual quantity, right? So we use the scale value that is the magnitude of V, and we use that to make a determination of what the unit vector itself would be. So a quick example. Let's say you have, I'll just keep it simple, vectors, or in R2, vector 3, 4. All right, and we're calling that, we'll call that V. All right, so if I want the magnitude of that, I'm going to look at the square root of 3 squared plus 4 squared. That's going to be the magnitude of V, or quality magnitude. All right, so you get 9 plus 16 is 25, root of which is 5. just plain old 5. All right. So my unit vector which we typically call u, but sometimes we use u for something else. So you might need to create a different value and call that the unit vector. You can call it whatever you want, but you could also just say unit vector equals, like I'm going to do here. That's going to be 1/5 of 3 vector 3, 4, which amounts to 3/5, 4/5. All right. Now, I'm just going to do a quick sketch. So I'm going to shrink and move this over a little bit. And pop that over there. I'll plot 3, 4. Keep it straight. That's so weird. It used to just kind of lock in the way I wanted. It's almost like it read my mind. All right, so actually, I only need the first quadrant, so I'm just going to move that down a little bit. So 3, 4 was my original vector. So I'll go 1, 2, 3. I'm trying to keep the spacing relatively consistent. So 3, 4 would be right about meh. And so just for convenience, I'll just label that V for vector V. All right, so that's my original vector. Now my unit vector, so this, 3/5 and 4/5, it's 0.6, 0.8. All right, so 0.6, 0.8. Write it like that because I need to estimate. And so when I'm looking to plot 0.6, I'm going to go a little bit more than half the distance. But I could also break up the interval from 0 to 1 into fifths. So 1, 2, 3, 4, kind of, maybe a little bit more like there. And then 1, 2, 3, 4. All right, so 3/5, 4/5, or I can say 60%, 80%, however you want to do it. But if I'm looking at this one, that's the 0.6, and this one would be the 0.8. All right, look at where they intersect. They're going to fall right on that line. And you're going to create a new vector that's going off in the exact same direction as the original, just it's got a magnitude of 1. All right, so it's identical in every way, just 1/8 its size. So that's the example. It's a good example, solid example. The very best example. No, it's an all right example. But we can verify it because the magnitude of the unit vector should be equal to 1. So it's going to be the square root of 0.6 squared and 0.8 squared. Or you can go with the fraction form. I just find it's a little bit more convenient to go with the decimal equivalent. Not always the case, but because the numbers are kind of nice, it just sort of works out that way. So we're looking at 0.36 plus 0.64. Add them up, you get a 1. The square root of 1 is equal to 1. So the magnitude of that unit vector is in fact equal to 1. And so, yeah, we didn't need to do that in order to find the unit vector, but to satisfy the curiosity of knowing, okay, is it really going to have a magnitude of 1? That's pretty necessary, right? At least the one time, right? Now, if we have a vector with a unit 1 that's living along the x-axis, we call that I. And one that's living along the y-axis, we call that j. All right. If we get the third dimension involved, which we will, we call it k. In the fourth dimension, you just keep going down the alphabet. All right. So we could also write our vectors, any vector, in component form, but using what's called a linear combination of the unit vectors I and j. Right. So it's actually pretty simple, to the point where it's kind of like, all right, is this really a step? Now, the rationale behind doing it this way is that it takes an expression that would be in those triangular brackets and it releases it from those triangular brackets so that we can use order of operations to combine terms. We can use calculus techniques to differentiate. So we're able to treat a vector the same way that we would treat a polynomial, right? So that's the justification for why we would do something like that. But the process here is, I think, is pretty straightforward, but I'll take you through an example or two very quickly, right? So when I have -2, 4, that could be thought of as the sum of -2, 0, and 0, 4. Now that -2, 0 has a scalar multiplier of -2. If I factor that out, I have a 1, 0. The 0, 4 has a scalar multiplier of 4. If I factor that out, I have a 0, 1. We define the 1, 0 as I and the 0, 1 as j. So this just becomes simply -2i plus 4j. All right. Now, in order to get the answer, you wouldn't have to show any of that work. That's just to understand why it works the way it does. Really, if you think about it, the x value gets an I slapped onto it. The y value gets a j value slapped onto it, and you just add them together, right? So you can just jump right to 0i minus or plus negative, I'll write the plus negative, 9j, which would then simplify down to -9j. You could do it like that, but if you start falling in love with shorthand or shortcut ways of doing things, then what you end up with is, all, technique and I guess you could say procedure, but no real understanding of the underlying concepts, right? So that ends up being kind of a big issue. All right. So vector u is a unit vector that forms an angle of 60 degrees with the positive x-axis. Use standard unit vectors to describe u. Right. So this is going to add in an extra layer because I'm saying it's got a 60-degree angle with the positive x-axis. We also do not know the magnitude. Right? Vector u is actually we do. Sorry, it's a unit vector. So the magnitude is going to be equal to 1. Right. So we're looking at, and if we want to use a standard form, magnitude of vector v cosine theta comma sine theta. But because it's a unit vector, I could just say 1, and then we'd have cosine 60 comma sine of 60, which cleans up to 1/2 comma radical 3/2. But if I'm using standard unit vectors in order to describe vector u, well, they said it's vector u, so this should really be a u. So this is my u. I want to get the ij stuff involved. I would be saying 1/2 I plus radical 3/2 j. All right. So it's really not that bad. It's just kind of building off of the stuff that we did on the previous page, just with this new IJ stuff. All right, nothing too crazy though. But what we're going to do now is apply this in a physics context. So start off with a simple example. A jet's flying at a velocity of 500 miles per hour due north when it encounters a wind blowing out to the west at 50 miles per hour. And I draw a diagram and use it to find the jet's resultant velocity to the nearest 10th. Right, so key here is draw a diagram, so let's start with that. Always a good idea anyway, regardless of whether they tell you to do it. So we're going due north and out to the west. So let me do that. So let's get some due north. I think it's straight. That's not. And then out to the west. All right. Now they give us the velocity. Now velocity involves magnitude and direction, but we'll just focus on the magnitude for a second. It's got a value of 500, right? And it's going in the northern direction, all right? And the wind is going out to the west at 50 miles per hour. What I'm gonna do is I'm gonna overlay a set of coordinate axes here. So I'm just gonna pop in a little XY axis. And I'm going to state the angles with respect to 0 degrees for each of these vectors. All right. So I have my vector going out to the north, and let me actually overlay that back on top of the overlay on the overlay, just so it stands out a little bit. So I got this angle here. I'll use an arrow to justify. That's going to be 90 degrees. Then I got this angle, which is 180 degrees, but let me do a better job there. Oh, that's even worse, but I don't think it's going to get any better, so I'm just going to leave it. That's 180 degrees, all right? The one going to the north, for lack of a better name for it, let me just call that N. And the one going out to the west, same deal, I'll just call it W, all right? So the magnitude of N, the velocity N, is going to be 500 miles per hour, so mph. The magnitude of W, these are supposed to only be positive values because they, you know, like it's magnitude, the double bracket means magnitude, but it also is a form of absolute value, right? So only positive numbers here. Any negatives are going to come up in the coordinate portion of the component vector, right? So that's going to be 50 miles per hour. All right. So I have those two pieces of information, and now what I can do is I can get the component form of vector n. So n is going to be equal to 500 times the cosine of 90, comma the sine of 90. And W is going to be equal to 50 times the cosine of 180, comma the sine of 180. Now we need to find the resultant vector. So that's next in the process. We can do it graphically, we can do it numerically. If we want a nice visual on this, I can come up with the opposite sides. So something like that is a little out of whack. And then use that to determine, oops, just can't. And it always walks on me at some point. All right, so this is my resultant vector. That's all well and good. So I know what, generally speaking, I mean, I've got kind of ballpark the figure, nothing's to scale here, but generally speaking, the direction of where n plus w would go, the resultant vector is the vector sum, right? Now, in order to perform these computations, or to get the result, I need to perform the computation. So what I would do is expand the n vector. So first I clean it up. Cosine of 90 is equal to 0. Sine of 90 is equal to 1. So 0, 1. And w would be equal to 50. Cosine of 180 is negative 1. Sine of 180 is 0. So n would be equal to, if I distribute it through, 0, 500. W would be equal to negative 50, 0. All right. So if I want the vector sum, I'm just going to add these two things together by components. So n plus w is going to be equal to the sum of the corresponding parts, so negative 50, 500. So then what I would need to do to find, so I got the resultant vector. If I want the velocity, I need the magnitude of that. All right, so I need the magnitude of n plus w, which in turn would be negative 50 squared plus 500 squared. So we'd be looking at, well, this is 2,500 plus 25 with 4 zeros, for 250,000. 250,000, you want to hold on to that one. All right, and so the square root of 252500, and at that point we can kick it on over to a calculator. Kind of went as far as some kind of record. I don't think I've ever made it this long into a class without having to whip out a calculator. But
First, can we just cut the squares and the radical? Isn't that like
the squares in the radical?
Yeah.
Oh, you mean like the 2,500 and the 250,000?
Yeah.
That would be breaking math rule 101.
No, I'm just saying, like, the squares. You just cut the radical and like.
Yeah, I don't think I follow. Yeah, because I was just going to pop this into a calculator and get the result.
Huh. That's okay.
So we're talking about 502.5-ish miles per hour. And so that would be our resultant vector magnitude, resultant magnitude, right? Yeah, so prior to that, before the expansion, if your question was, could you do something like this? And the answer would be yes. Yeah, that would have got the job done. I see way too many people that they do something terrible, and what they end up doing, and I don't think this was necessarily what was being asked, but I see people going from this step, so from here, and then coming up with 50 plus 500 because they took the square root of that and the square root of that, and they come up with 550. That's cardinal sin number 1 when it comes to math, right? Well, actually, that's not true. It's probably like number 7 because number 1 is incorrect canceling. But yeah, you definitely don't want to do that. So, but yeah, at any point, if you want to kick over to a calculator, that's fine as long as the question calls for it. I always just try to carry it through as long as I can without a calculator, just because sometimes the numbers work out nicely. You know, when they do, I don't want to rob myself of that satisfaction. It's just my thinking, but different strokes for different folks. Right, so that's a pretty straightforward example. There's other ways that you could have done it, and what a lot of people want to do is they want to draw the picture. Oh, that jumped on me. They want to draw the picture and then just use the Pythagorean theorem. You know, they get a 50, they get a 500, and then they use the Pythagorean theorem to find the missing side, and they call it a day. And that's, you know, like in an algebra class or a geometry class, that would have been great. The problem is that doesn't involve vectors in any way. So if you were to say, draw out a diagram, make a right triangle, and then just say 500 squared plus 50 squared equals c squared, and then solve, you haven't done anything with vector operations. So the point of the question would be vectors. So if you kind of skip over that part, you skipped over the part where I can give you any partial credit, right? So yeah, you just got to be really careful about that kind of thing, right? So just make sure that whatever approach that you're using stays within the spirit of the course material, because I've had a whole lot of people in the past, I mentioned this one before, saying that they want to use the physics rule, and the physics rule is great. The problem is if it allows you to avoid demonstrating the skills, or causes you to avoid demonstrating the skills from this course, then I can't give you any credit. Right? So I could talk to your physics teacher about getting you some credit in that class, but I can't give you any credit in this class. Right? So just something to keep in mind. Right? So on the next page, there's a bunch of examples, some more challenging than others. I want to save going over these for next class, because I think they're a good set of problems to go over after you've kind of tried to tackle them on your own, because all I could, end up doing here is just continue to drone on repeatedly, and it ends up not doing anybody any good. So you try those, and the next class I'll go over them with you. The answer key's online anyway, but the last thing I wanted to cover tonight is vectors in 3D, just the basic stuff, not too much. We're just the next couple of pages. It's very, very simple. We're going to stop just short of dot product, right? So, that'll kind of set us up nicely for the next class. But I wanted to sort of just get you going, thinking about what coordinates would look like in three-dimensional space. All right, so that's kind of where we're looking. So the orientation of the axes is probably the most important thing. You're just kind of getting an idea. GeoGebra is going to be a really useful resource when it comes to this, as you kind of get a feel for. As we move forward through the course, you start to get an idea that certain pieces of technology are useful for certain things. Desmos seems like a really good option when it comes to simple calculations, polar coordinates. Also, when you get to involve some parametrics, Desmos works out really nicely. But when you get to 3D, the GeoGebra ends up being the way to go, right? So so more on that later. We have some experience with it, but we don't have a whole hell of a lot of experience with it, right? Coordinate axes, when it comes to three-dimensional systems, always have your X and Y axes living kind of as a floor level plane. And then as an offshoot, going off vertically from the floor would be your z-axis. All right, that's your height. Right, so you think about 3 dimensions, you're talking length, width, and height. Right? What I do is normally when I'm in the classroom, what I'll do is I'll just kind of point to some corner of the room, you know, where the floor and the walls meet, and you look at that little corner, and you just find a corner in your own home, and you just look and you see you got the floor, then you got the walls coming in that corner. The corner of the wall going up, that's your z-axis, right? The baseboard on the floor going out away from the corner, though that would be your x and y axes, right? So you have positive x-axis, you have positive y-axis, and a positive z-axis, and corresponding with those, you have the negative counterparts, all right? So when I want to plot points, all I'm really doing is just kind of following the recipe that's laid out based off of the coordinate system. So this is going to be when I say 1, -2, 3. This is 1 unit along the positive x axis. Two units along negative y-axis. And then 3 units along the positive z-axis. All right, because saying things like left and right and down and up can be tricky. Down and up is actually the only thing that may be not tricky, but the left and right is like, well, which part is left? Which part is right? This thing's on an angle. You know, that's kind of crazy. But if you think about it as going along an axis, things start to make a little bit more sense. So what I'm going to do is I'm going to plot intermediate points along each one of these axes corresponding with the values in the order triple, right? So the coordinates. So I have 1 unit along the positive x-axis, that would put me right here. 2 units along the negative y-axis, so that would put me right here. And 3 units along the z-axis, positive z-axis, which is the trickier part, so I sit tight on that, all right? So focusing just as the 1 unit along the positive x and 2 units along the negative y, what I would do is I would create a parallelogram. Now, I actually have the grid here, so it actually makes it a little bit easier, but you'd normally create a parallelogram based off of the distance from the origin for each value, all right? So we treat it like a vector. So each one we treat as a vector, and then we use the parallelogram method, so there's a reason why I like that, to come up with some semblance of the resultant. It's not really the resultant vector, it's just the point that would be on the end of the resultant vector, all right? So I would have this one and this one, all right? So that would give me this location here, which is not my final answer. When I'm plotting this point, I still need to go up 3 units from that location, all right? So now what I would need is some indication of what 3 units along the z-axis looks like. I don't have a scale for that because it gets pretty confusing when you look at it, but that grid only applies to the XY plane, right? If I want to incorporate the z-axis, I need a fresh new scale for that. So what I'll do is I'll just make a scale with consistent spacing. Now, you label it any way you want, but if you don't label it, it's assumed to be going by ones, all right? And then when you do that, get an idea of what 3 units look like or looks like. That's what 3 units would look like right there. All right, so that's the distance that I'm going to go up from that red point that I plotted on the XY plane. All right, so this is what 3 units looks like. I'm going to take that distance and I'm going to drag it over here. I'm going to make it a, oh, I was going to make it dash, but I don't think I'm making it dash because that didn't work. You know what I can do? I use a white pen. And then plot a point at the very top there. That's the point floating in space, 1, -2, 3. Right, so that's the actual coordinate in space. And since we're only looking for coordinates, that's all we would need. If I wanted to create a vector, the diagram gets a little messier because then I'd have to draw a ray coming from the origin. So it would have to come from the origin here and extending to that point in space. So this is what vector 1, 2, 3 would look, 1, -2, 3 would look like. All right. So it's floating in space. It's just one of the big challenges when it comes to three-dimensional diagrams is the idea that, you know, we're producing a three-dimensional figure on a two-dimensional surface. It's naturally going to look a little off, right? But if you can somehow do it so that your diagram doesn't look so busy, you know, mine's starting to look a little busy. So what I'll do is I'll get rid of some of the fluff here. If you can do that, then it starts to kind of feel a little bit better. All right. So, you know, a little shading goes a long way too. So if I just do my parallelogram here, but shade it in. Well, it didn't really shade, but I can do it the old-fashioned way. So shade it in, and that kind of establishes that as the floor. It gives a little bit more perspective, and then it makes it a little bit more obvious that that point is floating in space above that floor. All right. That's, you know, that not really something I need you to do, but in terms of the shading and all that, it's just really more so that you can kind of, you know, I don't want to say it, but like not go cross-eyed when you draw your diagrams, because that's usually what happens. People look at it and say, I don't see it, you know, but a little bit of color, a little bit of shading goes a long way. Right. So when we talk about planes though, plotting, I mean, we're gonna talk about plotting points, lines, planes, just really anything geometric that you can think of, but in 3 dimensions. You know, if I tell you to draw something that's 2-dimensional in a 3-dimensional plane, you know, the only thing that's going to be different from the way it would normally look is that, like, if I make a circle that's normally in 2 dimensions, but I put it in 3 dimensions, you're going to be looking at it from a different perspective. So it might look a little bit more elliptical, but it's really not going to be anything other than a circle. It's when we get into 3-dimensional figures themselves, that's when things get a little crazy, right? But planes, we're focusing, or we had been focusing on just an XY plane, right? Now I'm saying that we have infinitely many planes that exist depending on the value of z. And z extends from -infinity to infinity. So we have infinitely many planes that are parallel to the XY plane, right? So if you kind of imagine, and maybe you could do a little bit more than imagine, you just draw a quick diagram. I'll just do it in some kind of space here. So you have your XY axes. Here's X and here's Y. Now, if I tell you that you have another XY axis right in front of this one, and then another one right in front of that one, and another one right in front of that one, and in front of that one, and in front of that one, and then I have many, many more even behind this one, then you start to get an idea that this XY axis, this set of XY axes has depth to it, right? So the best way we can do, or the only way really that we can do that in a 2-dimensional rendering, is to kind of offset it a little bit. So I'll do a little copy paste. And what I do is I just kind of 3D it. You know, that's where 3D images come from. You know, stacking one image on top of another on top of another. So like that. And that. right? So all of these X, Y axes are happening concurrently. And so you get texture and depth and thickness to all of this, right? So you could actually think of this as a floor, right? And that floor has, like I said, some thickness to it, right? So that's just a quick demonstration, nothing too crazy, but that's really getting at the idea of what a plane would be, or what infinitely many planes ought to look like. All right, so that it's tricky stuff when you're thinking of it, you know, like just with a lot of hand waving. That's why I try to draw the diagrams as best I can. I remember when I was a student, it was like just a teacher up on a blackboard trying to figure out a way. It's like, yeah, just kind of squint your eyes, turn your head to the side, and you see it, right? And we all just kind of faked it and said, yeah, because we didn't want to hurt her feelings. But nobody saw it, nobody understood. So with technology, it kind of helps. I mean, it definitely helps. But when you want to write the equation of a plane, if it's parallel to either the XY plane, the YZ plane, or the XZ plane, we have relationships and rules that we can kind of fall back on. So they're actually very simple. If I want something that's parallel to the the YZ plane, so we just reference the rule, it's X equals A, right? So whatever the X value is in your set of coordinates, that's what the equation of the plane is going to be. So X is equal to 3. And the reason why this is an important idea is because you look at X equals 3, as recently as a couple of weeks ago, that meant vertical line. Now it means a plane, because it's allowing X to be equal to 3 for all values of Y and Z. All right, so for all values of Y and Z. So it's infinitely, it's infinite in the in the Y direction, and in the Z direction, it's constant in the, where X is equal to 3. So if I'm drawing a diagram, what I would be looking at, and I'm just going to steal this one up above, I'll do it in green. Those keeping score at home. So here's X equals 3, 1, 2, 3. Oh, whoa, I don't even know. How did that happen? Here's X equals 3, 1, 2, 3. What I would be looking at is one sheet of paper or a rectangle that's parallel to the YZ plane. So here's the YZ plane. Here's Z. Here's Y. All of this space here, if you think of that as a wall, that's the YZ plane. It extends in every direction, so it goes back this way. All right, so all of that is YZ plane. It goes downward. So this is all the YZ plane. What I'm saying is that you have another plane that's parallel to that, just displaced 3 units in front of the YZ plane. All right, so that's the idea. We'll talk more about that next time. I'm looking at the clock now, and I realize that, yeah, we're gonna have to stop here because we're out of time. But more on that later, and I'll get GeoGebra involved so you can really see, because you know that's the best I can do with drawing and hand waving and all that stuff. But once you get GeoGebra involved, you see it's just a simple matter of putting GeoGebra in 3D and just typing in X equals 3, and you see that the plane, the appropriate plane, comes up. All right, so just something to keep in mind. It's a good, helpful resource, and you'll be able to use it on assessments, so you know that's a good thing. All right, so I'll stop the recording here.